Hello students, welcome to this lecture on the second part of the interconnects. So in the last lecture, we had seen one example wherein a driver which is a part of the subsystem module 1 was connected to the another inverter, or we can consider it to be a load. Um, so this being the load, and then this is we can consider this to be a subsystem module 2, and then this is the subsystem module 1. And it has been connected by a long 1 mm length of wire, and it has been characterized with a capacitance of 0.2 femtofarads per micron, and with a width and thickness of this particular value of 0.125 micron and 0.22 micron respectively. And we also calculated the resistance turned out to be 800 ohms for this long length of wire, and then the capacitance turned out to be 200 femtofarads. We had also seen this particular, the driver, the switching resistance, and then the parasitic capacitance of the driver side, and then the switching resistance, and then the input capacitance as well as the parasitic capacitance on this particular inverter. So this was the switching resistance for a normal unit NMOS, 10 kilo ohms, and then the parasitics for the coming from or extracted from the unit NMOS transistor was around 0.1 femtofarads. So for a 2:1, which is of the gate size of 3 inverter, we get the switching resistance as 10 kilo ohms, and then the overall capacitance seen at the output node, or the overall parasitic capacitance, turns out to be 0.3 femtofarads. So on the driver side, we have the parasitic capacitance multiplied by 10 times, and on the load side, we will have multiplied by 2 times the capacitance of 0.3 femtofarads. And then the switching resistance will get divided by 10 on the driver side, and then on the load side, it will get divided by 2. So this is what we have. So 1 kilo ohms switching resistance, and then 3 femtofarads is the total parasitics seen by this particular the driver inverter. And on the load side, we have 5 kilo ohms and then 0.6 femtofarads on the load inverter. With the interconnect resistance, switching resistance of 800, or rather resistance of 800 ohms, and then the capacitance of 200 femtofarads. Now, if I actually put all those resistance and then the capacitance of the driver inverter, of the interconnect, and also of the load inverter, this is the circuit diagram which we get. This is the RC circuit diagram which we'll get. So 1 kilo ohms is coming from the switching resistance of the driver inverter. With that of the 3 femtofarads is the parasitic capacitance. Now that is the input A, or rather, this input A could be this is the switching resistance of the NMOS or the PMOS transistors based on the input to the inverter. And then we have this 800 ohms. So we are using a pi model here of the interconnect. So the interconnect had a resistance of 800 ohms and then 200 femtofarads. So out of the 200 femtofarads, one part is going on this particular leg of the pi model, and another 100 femtofarads is going on to the another leg of the pi model. With the 800 ohm resistance is in the middle of this 100 femtofarads, the 200 femtofarads. And lastly, the 0.6 femtofarads is seen as an input capacitance of the load inverter. And then I have taken the 5 kilo ohms as the switching resistance, and then the 0.6 femtofarads as the parasitic capacitance is seen at the load inverter. Right. So this particular point A, it could be actually be VDD or to the ground. All right, based on the input to that of the driver inverter. If the driver inverter input is 0, this A value will be VDD. And we have all the capacitance to be charged, right? And then we should be able to find out the propagation delay for the rising one. If if the input to this particular driver inverter is actually 1, this particular A point will be connected to the ground supply, and that means that all the capacitance should now start discharging to the ground, right? So I have left it very, very generic in the sense that we need to estimate what is the propagation delay of rising or falling. So based on the input at the driver side, we should be able to estimate that. But if I keep it generic, then I should be able to find out the propagation delay. It could be rising or the falling. So the delay from point A to point B is what we will try to estimate that. So using the Elmore delay method, this is the resistance, and then the capacitance, these two will be in parallel. And then we will have 1 kilo ohms multiplied by 100 plus 3 femtofarads. Plus, this particular capacitance sees a shared resistance of 1 kilo ohms plus 800 ohms, so 1.8 kilo ohms multiplied by 100. And these two capacitance are in parallel, so I've taken not only 100 femtofarads, I've also taken 100 plus 0.6 femtofarads. So from point A to point B, it will be the summation of this product of RC. Turns out to be 103 picoseconds and then 181.09 picoseconds, 284.09 picoseconds. And the delay of the C to D, which is the next stage, will be nothing but 5 kilo ohms multiplied by this 0.6 femtofarads, which will give me 3 picoseconds. So if I put together, given at the input to the driver, any changes in the driver inverter on the input side, we will have the output at the point D, which is nothing but the output of the load inverter. So looking at the overall delay of these two stages, including the inverter, including the pi model of the inverter, we actually get 284.09 picoseconds plus 3 picoseconds, turns out to be 287.09 picoseconds. Right, so this is the delay with the interconnect, or this is the delay with the wire. Now, if I estimate delay without the wire, that means that the pi model, the R and then the capacitance, which was divided into two parts, and then we made the pi model. If that is not there, what will be the delay of the two inverters, the driver inverter and then the load inverter? So the driver inverter, can be is represented in the form of the RC circuit. So this is the switching resistance of 1 kilo ohms and then 3 femtofarads. And then this particular point is our B point, where we will get the input capacitance of the load inverter. So that will be 0.6 femtofarads. And then the load inverter's switching resistance of 5K, and then the 0.6 femtofarads as the parasitic capacitance. So we will get now 1 kilo ohms multiplied by 3.6 femtofarads and then 5 multiplied by 0.6. Turns out to be 6.6 picoseconds. With the wire, it was actually turning out to be 287.09 picoseconds. So coming back to the present slide, 287.09 picoseconds. So with the wire, and without the wire, the delay was 6.6 picoseconds. So it turns out that the interconnects actually dominate in the overall performance, or actually dominate in the estimation of the overall delay. All right, and then something has to be done to improve the performance or to reduce the delay. So in the last slide, what we had seen was the interconnects become very dominant in estimating the delay. For a simple circuit in this case, where an inverter was connected to another inverter, and if I have a long interconnect of 1 mm, the 1 mm line, the 1 mm copper wire, turns out to be more dominant, and it gives us an overall delay of 287.09 picoseconds as compared to around 6.6 picoseconds. It's a magnitude of 50 times more. Now here in this particular slide, we want to estimate what is the energy. So normally for a circuit, when we design, there are three actual parameters, three aspects of the design. One is what is the delay. The second one is what is the energy or the power. And then the third one, what is the footprint. So let's start thinking about what should be the energy that is being, that should be delivered by the rails, by the power rails for this particular wire to communicate or to transfer a bit of information from one end of the wire to the another end, right? And that particular energy, we call it as the switching energy, to send a bit of information from the power rails, in the sense the VDD rails. If I have, a capacitance of the wire characterized for that particular interconnect as 0.2 picofarads per unit length of the wire. So if the length of the wire is 1 mm, we can say that the overall capacitance of the wire is 0.2 picofarads. right? So what should be the energy that is being delivered by this VDD? And if I actually consider a simple model, the L model, which is R wire and then the C wire here, right? I can actually consider different models, pi models or in T model. But this L model turns out to be very, very simple to understand, and that's why I have used here in this particular slide. So if VDD is connected to the resistance of the wire and then the capacitance, the energy that is being delivered by the VDD is actually turns out to be C wire VDD square. The energy delivered by the VDD rail or the power rail. The energy consumed by the C wire turns out to be half C wire VDD square. The remaining half C wire VDD square will be dissipated as a heat from this resistance R wire. So the energy that is being consumed by the C wire will be half. The energy dissipated by the resistor will be half C wire VDD square. But the overall energy that is being delivered by the VDD so that the C wire gets charged to VDD will be nothing but C wire VDD square. Alright. So the overall energy that is being delivered by the VDD rail turns out to be in terms of the C wire, the capacitance per unit length multiplied by VDD square. So it will be nothing but 0.2 picofarads per millimeter multiplied by 1 square, 1 voltage square. So finally we will get in terms of energy, the unit will be 0.2 picojoules per millimeter. Right. So if the length of the wire is 1 mm, then we can say that the switching energy that is being delivered by the power rail is 0.2 picojoules. Right. If it is 1 mm of wire. If it is 2 mm of wire, it will be 0.2 picojoules multiplied by 2. So hope this is clear. Moving ahead. So let's see an example here. It's a very realistic example where we have a die, where we have a chip of 20 mm cross 20 mm size. And we have a lot of wires here. The pitching between the wires, or rather I will say that the average pitching of the wires, pitching in the sense the distance between or the spacing between the wires, the individual wires or the neighboring wires is around 250 nanometers. Overall, this particular dimension is 20 mm. So the number of wires in this particular case will be nothing but 20 mm, 20 millimeter divided by the pitching, which is 250 nanometers. So I will get the total number of wires that is being present in this particular die. And let's assume that we have only vertically placed wires. We don't have horizontally placed wires at all. Right? So we have only vertically placed wires. This die is actually running at a frequency of 3 gigahertz in a 65 nanometer technology process with a pitch of 250 nanometer. That is something we have already seen. And the another information is half of the available wire tracks are used. So what it means is whatever is the number we get, 20 mm divided by the pitching 250, we will get the number of wires. So the number of wires, if it is n, only half of this will be utilized. The other half is not at all utilized. Right? The other factor is the activity factor is given. And then the CW value, which is 0.2 picofarads per millimeter, is being characterized for the wires which are there in this, which are designed in this particular die. All right. These wires may have connected to different transistors or different circuits, but we are ignoring the circuits at this point of time. We will say that only the wires, what is the overall energy that is being consumed. Right. So the additional energy is actually consumed by the computational blocks because of the transistors or whatever is the design, whether it's a NAND gate or an adder gate or a multiplier gate will be there from one end to the other end of the wire, so that will be connected. But what we are saying is we are ignoring the computational blocks, the logic blocks, and we are only interested in how much is the energy that is consumed by the wires. So let's look at this activity factor. The activity factor is stated as 0.1. What it means is, it is, let's say that I have 10 wires, 1, 2, 3, 4, and then 10th wire. So 1, 2, 10 wires. Out of this 10 wires, at a particular time, let's say that only one wire is where, the logic block is sending the signal. Okay, sending the signal in the sense the logic block in this particular wire is now transitioning from 0 to 1, and then that has to be propagated to the other end of the wire. All other blocks has a are having a steady state voltage, so there is no change in the signal, there is no change in the voltage level. All right. At another instance, we will have one more wire changing the signal at one end, and that has to be communicated, that has to be transferred to the other end of the wire, right? So the activity factor says that on an average, the probability that the one end of the wire, out of the 10 wires, only one wire has to transfer the change in the transition from 0 to 1, right? So in that sense, the active wire activity factor says that if I have 10 wires, out of that only one wire is needs to supply that amount of energy to transfer the signal, to transfer the transition of 0 to 1 from one end to the other end. All other 9 wires doesn't have any transition. So the activity factor in that case, it is given as 0.1, which says that 1 in 10 wires is likely to do the transition, and that energy has to be supplied for that particular wire, right? So what we say is, from the n by 2 wires, whatever is that number, right, only 10% or 0.1 of the n by 2 wires needs that particular energy to be supplied, needs that energy to be delivered by the VDD rail, so that the proper transition from the at one end of the wire will be reflected at the other end of the wire, right? Hope this is clear. And of course, the wire capacitance of the wire is characterized to 0.2 picofarads per millimeter. So let's try to evaluate and reach out to what should be the energy that needs to be supplied by the VDD. So the number of wires, n value, is nothing but 20 mm divided by 250 nanometers, which turns out to be 80 multiplied by 80,000 basically. So 80 multiplied by 10 raised to 3. Half of the wire tracks are used, the other half is actually not at all used. So it is 40 into 10 raised to 3. So the overall capacitance I've calculated for all the wires put together, 40,000 of wires which are being used, turns out to be 40 into 10 raised to 3 multiplied by this factor of 0.2 picofarad per millimeter of the length. So picofarad per millimeter, so I have actually written it as femtofarads per micrometer multiplied by the length of the wire. The length of the wire is anyways 20 millimeters, so that's what I have written here. So overall capacitance of 40,000 which are in usage turns out to be 160 nanofarads. Right, hope this is clear. So finally, the energy delivered is nothing but the activity factor alpha W of the wire, the activity factor of the wire, the total capacitance, which is 160 nanofarads. So 160 nanofarads. Activity factor is 0.1, and VDD is nothing but 1, the whole square. So VDD square. So it turns out to be, so the energy overall turns out to be 16 nanojoules. If the frequency is given, so let's also try to estimate the power. So the power delivered will be nothing but the energy, divided by the time period of the clock signal. So in that sense, if the clock time period is not given, but the frequency is given, so we can say that it could be multiplied by frequency, and then we will get 16 nanojoules multiplied by 3 gigahertz. So the overall power turns out to be 48 watts. Just by the wires, and then we have not even accounted for the computational blocks that are there in this particular die. And we are also talking about only one level of the die. There could be multiple dies which are stacked in a 3D manner, and so the overall power is actually, it turns out to be very, very huge, and it is mostly, in this particular situation where there are multiple wires, it is always the energy or the power is actually dominated by the wires and not by the computational blocks itself, right? So that's what I've written here. Note, this is one layer, and multiple layers will add more power dissipation by the power rail, only for the wire to transfer that particular the logic from one end to the other end, or the whatever the transition that happens from 0 to 1, that has to be transferred to the other end of the wire. And only for doing that, the power that is being delivered by the VDD rail turns out to be 48 watts, which is kind of very, very huge. And this is the major problem in today's SoC design, the system on chip, because there we see highly dense, the high density of the wires that is kind of running around in the chip design, and that has to be resolved, right? The other important point here I wanted to make is, why is this frequency coming into the picture, or why is the clock time period coming into the picture, right? So we have actually used the activity factor, and activity factor, it's basically it is it is basically a probability for the number of the the amount of the, or the number of the wires within a group of the wires where it is doing the transition, right? But for the power to be calculated, we always consider it is nothing but over the average time period, right? So whatever energy we estimate, and if I actually do the average of the energy over one particular time period, that should give me the power. So the power is always with respect to the energy divided by the time. So this particular time is nothing but we consider it for a one particular clock time period, right? And then normally for a chip design, we will have usually we will have a limited number of clocks. To be at a primitive level, what we are seeing is we will have one particular clock to be designed, and we will measure the power with respect to this particular clock. Now that particular clock frequency is given as 3 gigahertz, and hence we actually do we estimate the power with respect to that particular clock frequency. So energy multiplied by that particular clock frequency is our 48 watts.